This is my lab 1 report for Physics 2211 on constant velocity. The purpose of this lab was to demonstrate our understanding of constant velocity when there's a constant force involved. We did so by observing the motion of some object that's moving at the same speed without changing direction. And we also had to create and compare our recorded observations with a computational model using GlowScript. The fundamental physics principles that you must understand in order to complete this lab, or even understand it, are Newton's first and second laws, the position update formula, and the velocity update formula. Newton's first law simply states that an object at rest or motion will stay at rest or continue to be in motion in a straight line unless acted on by a net external force. Newton's second law states that the rate of change of momentum of a system over time is directly proportional to the force applied. The velocity update formula is stated right here, which is just final velocity equals initial velocity plus the net force divided by mass times the change in time. The position update formula, stated right here, is just simply the final position is equal to the initial position plus the velocity average, which is just the change in position divided by change in time multiplied by the change in time. And this was our setup for our experiment. We used a meter stick in order to have a realistic scale to use while we were in the tracker, a wheel of yarn as our system and the object that we'd be analyzing. We of course used tracker for analyzing the motion, GlowScript for creating the computational model, and then we also had surroundings as well, which was the applied force, gravity, and friction. Assumptions that we're going in with is that there are no air resistance or friction, and that a flat table is used so that the normal force is equal to the gravitational force. And a note, we are only observing displacement along the x-axis, not the y or z-axis. This is just a quick video of our wheel of yarn going across the meter stick. And now this is my data. The x-axis represents time, the y-axis represents the x dimension of the object over time. With such an upward sloping linear graph, it makes it appear that the wheel of yarn is moving at a constant velocity. But how do we check for sure? In order to check for sure, we must use our computational model in GlowScript. We set the ball's initial position and velocity values to the corresponding values that were in our graph. And then once you do that, we used a while loop that would end at the final point in time at which the wheel of yarn crossed the final portion of the meter stick, and then the net force would be equal to 0, since it should be a constant force. After that, the ball's velocity and position would be recorded each time. What were our results? The blue line equals the observed position, and the red line equals the predicted position by the model. Initially, it was an underestimate, but we can see the trend that it'll be an overestimate as time moves further forward. The possible errors that we could have had in this experiment are the outside forces such as friction that could play a big role, for instance if the table is too rough or jagged. Another big error that could have played a role are GlowScript or tracker miscues. Incorrect tracker inputs, wrong numbers inputted into the script program, or inaccurate position tracking. What if x was flipped? Not much would change except for the slope of each graph, going from positive to negative. And then what does all this mean? Are we able to know how many different pushes or pulls are being added together to give a net force of 0? Not necessarily, and it isn't necessarily possible to accurately pinpoint that number either. Because we know that to give a net force of 0, there are likely several external forces that could be at play. For instance, friction between the table and the wheel of yarn. Furthermore, there's no way of preventing these forces from occurring. It is due to these external forces that the computational model begins to overestimate the position over time, especially as time continues.